The Virgo, that's a gravitational wave detector in Italy, and it's part of a larger network of global gravitational wave detectors. They had their very first huge discovery in 2019, which was just when I started my PhD. So that was a really exciting period. The project was about developing a model for a noise source in the detector that is very closely related to the seismic conditions at the detector site. It describes how the mirrors in the detector move with fluctuations in the seismic field, how they are attracted to it. Signal is injected in the detector, which looks like a gravitational wave signal, but it actually comes from these seismic fluctuations. So the goal of my research was to develop a model that describes the detector site from a geological point of view. Models existed so far, but due to computational limitations, they were quite simplistic. So for example, they assumed that the underground at a certain detector site only consists of one material, but this is not really the case. What I achieved is to make a model that consists of a horizontally layered model with different materials, and it also takes local noise sources into consideration. And then the goal was to apply that at two different detector locations, at the Italian site at Advanced Virgo and the Einstein telescope candidate. So for the Advanced Virgo site in Italy, that's very close by to Pisa, we conducted a 2-week-long seismic array study. So part of my project was actually go there into the fields for a couple of days and stick seismic sensors into the ground. And we left them there for a couple of weeks, and then we had to refine them, which was quite challenging, but we did refine 62 out of 64, so that's a good score. The other site we studied intensively is the Dutch Einstein telescope candidate site in Limburg, where we also conducted several seismic array studies. But the Einstein telescope detector will be located underground. So what we also conducted is a borehole study to a depth of 250 meters, where we also placed seismometers underground to get an impression of the geology and the wave speeds on surface and at 250 meter depth. At the Virgo site, we learned the following thing. So what you see here in the thick black curve is the sensitivity curve of Advanced Virgo. And the dashed curve is the Newtonian noise that was inferred previously from the more simplistic models. And my result is this thick blue curve. The blue Newtonian noise from the new model is especially at high frequencies below what was assumed so far. The noise was so far actually way overestimated. At the Einstein telescope candidate site in Limburg, we learned a huge amount about the geology, especially that even though it is noisy on the surface, it's very quiet underground. And what you can see is, which is really nice, is that it is compliable with Newtonian noise standards that are necessary for a site to be suitable for a Einstein telescope candidate site. Limburg is suitable from a scientific view to host the Einstein telescope detector, which is a fantastic result.